Hi, everybody. Good to see you. Good to virtually see you, of course. I want to continue our discussion of polynomials. And at this point, we've really looked at their graphs. We've looked at some features of the graph as manifested in the algebraic form or equation of a polynomial. And when we've done that, we've really switched between the standard form, you know, an x to the n plus and all the way down to you get your constant term. Or we've looked at polynomials that are factored. We haven't gone between the two. Now, if you're sitting in a pre-calculus class, then you've been through algebra, obviously, and know how to factor quadratics, which, you know, is a degree 2 polynomial. And you know that they can't always be factored, but when they can, you have a way to do that. What we want to do now is expand that. We want to look at roots more generally. And of course, the roots are easily found when we have a factored form, as we saw with the factor theorem, right? If I have a linear factor, then I know what the root is. So can we take a polynomial in its general form, its standard form, and rewrite it in factored form? That's what we want to do. This is going to involve something known as the rational roots theorem, because we're looking for rational roots, and it's going to involve some division. So let's go ahead and get started. Okay, so we're looking at roots of a polynomial. And like I mentioned, right, you have some familiarity with using, with finding roots using like the quadratic formula or being able to factor. But we want to expand this now. So we want to find ways to factor any polynomial. And what's interesting is that, you know, you have a quadratic formula, right? Which means if I let my roots be irrational, if I let my roots be complex, then that quadratic formula I could use to find the roots of any quadratic equation you could think of. That's a generalized formula, right? It's a simple recipe. Plug and chug and boom, you got the roots. Interesting though, once you get to degree 5, anything past 4, it's an interesting result of algebra that there is no generalized method. And that's a wonderful result. And you know, if any of you guys are math majors and wind up taking an abstract algebra class, you'll certainly look at that result. So it's kind of interesting that while we have the quadratic formula, it's really the notion of having a formula to solve for roots of a polynomial really gets expended by the time we move past degree 4. Okay, so here we have the rational roots theorem. And so suppose we're given a polynomial and the coefficients are integers, so all those are integers. Then there exists integers p and q such that p over q is a 0 of p of x, or a root. Well, what do p and q come from? Well, p is a factor of the constant term. Q is a factor of the leading coefficient. So if I have a rational root, it has to be of the form p over q. So take a factor of the constant term, take a factor of the leading coefficient, and one of those, if I were to list all possible factors of each, and therefore all possible quotients or ratios, one of those will be a root if there's a rational root. So in other words, it gives us a list of candidates. And we're going to go ahead and prove this and kind of see how this plays out. But before we do, let's see that this is true in a specific case. A little real-time editing there. So here's an example. We have this polynomial. And so my p's, right, my constant term is -3. And so my p's, right, would be plus or minus 1, plus or minus 3, okay? My leading coefficient is 6. So my q's are going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And so what this means is I have a list of candidates, okay? And so I take all the possible p's over all the possible q's. So let's start with plus or minus 1. Well, 1 over 1 is 1, so plus or minus 1 is a possibility. 1 over 2, so plus or minus 1/2. 1 over 3, so plus or minus 1/3. And 1 over 6, plus or minus 1/6. Now let's move to the 3. Well, so 3 over 1 is 3, so we got plus or minus 3. 3 over 2, plus or minus 3/2. 3 over 3, which is 1, we've already got that. And 3 over 6, we already have that as well, because that's 1/2. So I've got, let's see, 1, 2, 3, 4, 5, 6, plus or minus. So I have 12 possible rational roots. Okay, and so now I can just try them out, right? I can guess and check. So if I say x is equal to 1, well, what's p of 1? Well, I don't really care what it is specifically, unless it's 0. I can look at it and I see it's not 0, so I don't care. Well, what about, I don't know, let's keep trying. Let's say, and I'm just guessing here, literally. How about negative 1/2? Well, if we have negative 1/2, then we're going to get p of negative 1/2. Well, it's going to be 6 times 1/4. Yeah, I can already tell that's not going to be 0. Okay? And we can keep trying. So maybe we try next. Let's see here. Maybe we try 3/2. Guess what? That's not going to work either. And so, you know, I'm not going to make you go through this, but it turns out that none work. Okay? None work. And so that tells me there are no rational roots. And you could see this work out in the quadratic formula. Okay, so I'm gonna clear my ink here. I'm claiming, you know, based on the rational root theorem that there aren't any rational roots. Well, let's use the quadratic formula, right? Because that's what we know will work. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And so we have negative 1 plus or minus the square root. And then what do we have here? We have 1 and then plus 72, square root of 73 all over 12. These two numbers are irrational. Okay, so there we see that it agrees. All right. So let's look at the proof. So we're going to say that p of x, and again, I need an arbitrary polynomial. So when I say arbitrary, it needs to have arbitrary degree, hence n, degree n. So a1x plus a0, okay? And so let's suppose, okay, suppose p over q is a rational 0 or a rational root. And we'll also suppose that it's in lowest terms, right? So it's been reduced, okay? Okay, so we have this term. Now, what does that mean to be a rational root? Well, that means that if I plug in P over Q, if I plug it in, what am I going to get? So P over Q to the n minus 1 plus A1 times P over Q plus A0. That tells me that this equals 0. Okay? All right. Now, if I multiply each side by Q to the n, then I'm going to get AN P to the n. Right? I'm just multiplying by Q to the n, and you'll see why in a second. P to the n minus 1 Q. And then as we move down, we'll get to A1 P Q to the n minus 1, and then plus A0 Q to the n. Okay? Now, I'm going to subtract and factor. Okay? I'm going to subtract and factor. So first I'll subtract my constant, because remember what I'm doing here. I'm trying to show that P is a factor of the constant term, right? And so to do that, I need to show that it's equal to the constant, that P times something gives me the constant. So equals negative A0 Q to the n. And then I can factor a P from this left-hand side. Okay. P to the n minus 1 plus a n minus 1 P to the n minus 2 plus all the way down to A1 Q to the n minus 1. Okay. And so what we have is we've shown, so what we have is P is a factor of negative A0 Q to the n. And what do we know about P over Q? P over Q is in lowest terms. So P is a factor of A0 itself, okay? Now this just shows that P is a factor of the constant term. I would encourage you to give it a try showing that Q is a factor of the leading coefficient. It's a very similar argument and kind of mirror this, okay? So there's the rational roots theorem. So let's see what this does for us. We're going to find all roots of this polynomial. Now, when you look at this, you should notice that you can't just go factoring this. And so what I need to do is find my candidates. So for my P's, I look at the constant term, 20. Well, what are the factors? Plus or minus 1, plus or minus 2, 4, 5, 10, and 20. Now for Q, we're looking at the leading coefficient, right? That's where my Q's come from. So plus or minus 1, plus or minus 2. And so my candidates are all the P's over Q's. So plus or minus 1, plus or minus 1/2. And then we move to the 2. Plus or minus 2. 2 over 2 is 1, so I don't need to repeat that. And now I move up, let the numerator be my 4. So plus or minus 4, 4 over 2 is 2. We've already got those. Move up to 5, plus or minus 5, plus or minus 5 halves, plus or minus 10, and then 10 over 2 is 5, so I've already got that. Move up to the 20, plus or minus 20, and then 20 over 2 is 10. We've already got that. And so now we're going to go through here and we're going to check. And I'm going to use synthetic division to do this just because it's so much simpler. And you know, I'm gonna start with some hope. It's not that I don't like fractions, but I think we all are hopeful that we get some nice integer solutions. So, you know, when you look at the number 1, for example, you can probably just eyeball it, right? I look at 1, and so 2 minus 3. There's no way that I'm gonna have 1 as a root. Okay, so I'm gonna maybe try 2. So let's try 2. And so my coefficients are 2, negative 3, negative 39, and 20. And here we go. 2 times 2 is 4. Negative 3 plus 4 is 1. 2 times 1 is 2. And you can already see that this is not going to work. Okay? And so we say, all right, that didn't work. What about, I don't know, how about we try 4? Why not? So 2, negative 3, negative 39, and 20. We have 8. Negative 3 plus 8 is 5. 4 times 5 is 20. And oh, that's not going to work either. Okay? And so we're going to, I don't know, I'll do one more before I let the cat out of the bag here, but maybe negative 4. And so if I have negative 4, my coefficients are 2, negative 3, negative 39, and 20. We have a negative 8. Negative 3 plus negative 8 is negative 11. And we get a 44. And negative 39 plus 44 is 5. Negative 20. What do you know? So there we go. Now, 2, negative 11, and 5. This is good because remember, this is really quadratic. And once I have a quadratic, sorry, 2x squared. Once I have a quadratic, I can factor. See, I found a root of negative 4, which means my p of x I can write as x plus 4 times, and then my quadratic polynomial, 2x squared minus 11x plus 5. And then, since it's quadratic, let's just go ahead and either use the quadratic formula, or let's go ahead and try to see if it'll factor. And so I'm kind of hoping this will factor, especially since I've got a 5 and a 2. That's going to get me to 10. 1. Does that work? Negative 1x minus 10x? It sure does. Okay? And so now, right, my roots, I've got negative 4 from my first factor. 2x minus 1, that's going to give me x equals 1/2. And then x minus 5, that's going to give me a root of 5. So sure enough, I got my roots. It started with the rational roots theorem, right? Finding 1. And then once I have a quadratic, I'm home free. All right? Very good. How about this one? So here, my p's, my constant term is 1. So that's pretty convenient. My q's, plus or minus 1, plus or minus 2. So let's see what my candidates are. Well, plus or minus 1, plus or minus 1/2. It's not so bad. Let's see what we get. So again, if I eyeball 2, let's see, if I eyeball 1, I'm going to get a 2 minus 7, which is negative 5. That's not going to work. What about negative 1? So if I have a negative 1, that'll make my first term negative 2. Nope, that's not going to work either. So I'm going to try 1/2. So let's put 1/2 up here. And let's see what happens. 2, -7, -2, and 1. So 1/2 times 2 is 1. -7 plus 1 is -6. 1/2 times -6 is going to be -3. -2 plus -3 is -5. And that didn't work. And so does that mean that the root must be -1/2? Well, not necessarily. Okay, we don't want to take that for granted, but because there could be no rational roots. But let's just see. We don't have a way to tell that yet. So -1/2 times 2 is -1. -7 plus -1 is -8. We get 4, 2, -1, and 0. Oh, good. And so -1/2 is a root, which means my p of x I can now write as x plus 1/2 times 2x squared minus 8x plus 2. And I'm going to actually factor a 2 out so that I have x squared minus 4x plus 2. Now I know that there are no more rational roots. I had 4 candidates. I tried all of them, and I only got 1 to work, which means this quadratic factor, I need to use the quadratic formula on. So that guy is going to get the quadratic formula. Okay. And so x equals -b, 4, plus or minus the square root. And then b squared will be 16 minus 4 times 1 times 2, all over 2, which equals 4 plus or minus the square root of 8, all over 2. Forgive me, I'm going to get rid of this work over here since I already found it. And so what do we have? We've got 2 plus or minus, well, 8 is 2 root 2, so 2 plus or minus root 2. So I've got my roots. My roots are -1/2, 2 plus root 2, and 2 minus root 2. Okay, there we go. Okay, now, it's nice that we have a way to get candidates because, you know, you could have, there are infinitely many numbers, but if I can pare them down to some finite list, then great. But even that finite list, right? I mean, let's think about this. I could have a list 1,000,000 long. That's finite. I could have 1,000,000 candidates. That's finite. Computer could probably do that pretty quickly, but that's still a pretty long list. So is there another way, or not another way, but is there another layer we could add to this to say, okay, I've got my candidates. Can I pare that down even more? And so, of course, there is. Otherwise, why would I be talking right now about this? And so let's look at this polynomial here, and then we're going to employ some additional help here. We're gonna look at some work attributed to René Descartes, famous French mathematician, and see what happens. So here's a couple new theorems. Descartes' rule of signs. So all of these are going to come from division. When we divide synthetically, let's see what happens. Okay, we'll know that as we move along. So Descartes' rule of signs. The number of positive real zeros is equal to the number of sign changes, or less than that number by an even whole number. Okay, so if there are, say, 5 sign changes, then the number of positive real roots is either going to be 5 or 3 or 1 or so on, okay? And then the number of negative real zeros is equal to the number of sign changes in P of negative x, or less than the number of sign changes by an even whole number, okay? And then we're going to pair that, and unfortunately the proof is a little bit beyond the course, so I'm gonna hold off on the proof. Then we have upper and lower bounds, right? I've got this big list, but can I find a lower bound and an upper bound? And so when we synthetically divide, and I look at that row with the quotient, if there's no negative entry, then B is an upper bound. If I divide and the row that contains the quotient and remainder alternates, then I have a lower bound, okay? And if the entry is 0, we're just gonna let it be whatever makes the pattern continue, all right? We're okay doing that. And again, this is a nice result. The proof is a little beyond the course, so I'm not gonna actually go through that. But we can sure put it to work, okay? And so if you look at this example, right, my candidates, let's just think about this for a second. If I were to list my candidates or build them, I need to start with my p's. Well, I have a constant term of -40. So let's see, these are all my factors of 40. And then I have my q's, which are going to be my factors of 30. So plus or minus 1, 2, 3, 5, 6, 10, 15, and 30. So I just need to take one of my p's over one of my q's, do all possibilities, and those are my candidates. Yeah, no thanks. Okay, that's a big list. I don't want to do that. Okay, so let's instead, I'm going to keep this in mind, just these p's and q's individually, but I'm not going to list out all my candidates. Let's start with Descartes, okay? Descartes' rule of signs. So P of x. Well, P of x is 30x cubed plus 79x squared minus 6x minus 40, okay? There is one sign change. Okay, one sign change. So that tells me there is one positive 0 or 0, okay? And then we look at P of negative x. Well, if I plug in a negative x, that becomes a negative 30x cubed. The square doesn't change signs. The negative 6x changes signs. Okay. And so I've got one sign change, two sign changes. Okay. And so that means there are two negative zeros or none. Okay. And so now I'm going to see if when I synthetically divide, so I'll make this note, when I guess and check, I will find lower and upper bounds. Okay. So what do I mean by that? Well, I will show you. So let's say I try -1, right? That's one of my candidates. And so I come down here, I get 30, I get 49, this is going to be negative, and so on. So this isn't going to be a root. And if you look back at the lower, or the, oops, too far. Alternates non-positive and non-negative, then I get a lower bound. Because I'm in this case, right? I have a negative root, negative candidate. Well, look, this thing already does not alternate because I've got positive, positive. And so that's not going to serve me for a lower bound. And so maybe I try -5. So let's see what happens with -5. Well, 30, 79, -6, -40. And then what's going to happen? Well, -5 times 30 is -150. So then I'm going to get a -71. Oh, that's encouraging. I'm going to get a 355, a 349. Well, -5 times times 349 is a negative number. I'm going to have a positive plus a positive. I'm sorry, negative plus a negative, which is going to give me another negative. I don't really care what it is, but I have sign changes, right? Positive, negative, positive, negative. Because of that, -5 is a lower bound. Okay, so if you think about my list of candidates, that gets rid of 40, 20, 8. I'm sorry, I'm going the wrong way. It's a lower bound. So that gets rid of -40, -20, -10, -8, and -5 as well, right? Since that didn't work out. So I have a lower bound now. Now, similarly, right, I could then play around with an upper bound. And so let's say I try 1. And so I try 1, and let's see what happens with 1. 30, 79, -6, -40. Now remember, for an upper bound, no negative entry, okay? So if I have no negative entries, 1 is an upper bound. Well, let's see, what am I going to get? Well, 79 plus 30 is what, 109? And then we have 109. -6 plus 109 is 103. And this will be 63. These are all positive. So 1 is an upper bound. Okay. Well, look what's happened to my list, right? I had that big list of candidates, and now from here, I know that my root must be between -5 and 1, okay? So now when we go back to our list, let's go check it out. Let's actually see what some good choices are, right? We can eliminate some choices, right? 1 is my upper bound. That gets rid of 40, 20, 10, 8, 5, 4, 2. All right, this is very good. And 1 as well, because right, there was a remainder when I did 1. Okay. So let's go to it. Let's try and see what else works. So I'm going to get rid of these markings, and we're gonna do some guesses here. Whoops. So I'm going to try 2/3. Okay, so we have 30, 79, -6, and -40. Okay. And so 2/3 times 30, well, that's going to be what, 20? And then 79 plus 20 is 99. And so what is 2/3 of 99? Well, 66. And then we get 60. What's 2/3 of 60? Oh, 40. What do you know? Okay. And so this tells me that my polynomial is now x minus 2/3 times 30x squared plus 99x plus 60. I have a quadratic, so I'm home free. I am going to factor a 3 out, though, just because I want to deal with a slightly simpler quadratic. So 10x squared plus 33x plus 20. And then, again, we take this quadratic and we look at the quadratic formula. Okay. And so x equals negative b plus or minus the square root, and then b squared minus 4ac. So 33 squared minus 4ac all over 2a, 2 times 10. So let's see what we get. Let's see, 33 squared minus 4ac. 289, so negative 33 plus or minus the square root of 289 all over 20. And the square root of 289 is 17. What do you know? Okay, and so negative 33 plus 17 all over 20. Well, that's going to be negative 16 over 20, which is negative 4/5. And then negative 33 minus 17 over 20 is going to be negative 50 over 20, which is negative 5/2. So I now know my roots. My roots are 2/3, negative 4/5, and negative 5/2. All right. So I realize that there's a lot of work involved, but I want you to just take a moment. Picture yourself finding your P's and Q's, and then you're checking them. You're doing that synthetic division, checking if the remainder is 0. You're going through, you're going through, you're going through. What these last two theorems, Descartes' rule of signs, and really the upper and lower bound theorem tell us is how to interpret what our non-roots are telling us, right? If I do a synthetic division and I alternate signs in my quotient and remainder line, that's great. That tells me something that bounds my roots. If they're all non-negative, oh great, now I have an upper bound for my roots. So that big list of candidates that you're working through gets shrunken down. You don't have to look for it automatically when you have your list of candidates. Just start processing your candidates, and as you do, you'll discover that when certain things happen, you can zero in and eliminate much more than just the root that you had tried. Okay, so there it is. And also notice that once you get to a quadratic, we are home sweet home. All right. So work on these, go back and look at my examples and try some. And as always, I wish you the happiest of studies.